This presentation is intended to remind you of some of the major themes we have talked about thus far in the class. We will start by recapping the fields of descriptive and inferential statistics. Descriptive statistics focus on the tabulation, presentation, and summarization of measurements. Simply put, this focuses on describing a sample. We have talked about the real-world limitations that make conducting a census unfeasible, leading us to collect a sample and use inference to make a conclusion about the entire population. The field inferential statistics utilizes techniques to make generalizations about a population from a sample by estimating population parameters and testing hypotheses. Now we will review what a normal distribution is and the probability theory that allows us to utilize its concept in sampling. A normal distribution, or the normal frequency curve, is generated by the displayed equation. Although this equation is important and generates the shown distribution, I will never expect you to memorize such things. I do, however, expect you to remember that the math of a normal distribution results in a symmetrical, bell-shaped curve around the mean. For each population mean and standard deviation, there is a normal distribution curve generated. This means that the mean controls the middle location of the distribution, and the standard deviation controls the width of the distribution, with a larger standard deviation resulting in a more spread out distribution. If we roll a pair of dice 10 times as a sample, we get the following set of values: 10, 4, 12, 10, 11, 4, 12, 4, 7, 9. From these, we can calculate the sample mean as 8.54, which differs from our expected population mean of 7. But if we roll that pair of dice, say 200 times, probability tells us our sample mean should approach the population mean, and we can see that eventually it does. This foundational assumption of all probability-based sampling is called the law of large numbers, which states that as the sample size increases, the sample statistic will approach the population parameter regardless of the population distribution. Now let's look at the set of 10 dice samples in a slightly different way and take 10 independent sets of 10 dice rolls. We should think of the average of each sample set corresponding to a possible value as belonging to a distribution we call the sampling distribution of the mean. If we look at how the mean of the means from the sets of samples changes, it approaches the population mean fairly quickly. Once we take a sample that is large enough to average out outlier values, the sample distribution of our statistic will be normally distributed, where the sample estimate of the population mean will be approximately the population mean, and the standard deviation of the statistic will be represented by the standard deviation divided by the square root of n, which we more commonly refer to as the standard error. If we think about the pair of dice experiment, we get these curves for the variable distribution, which represents the possible outcomes of a single sample, and sample distribution, which represents the possible sample means if little n equals 10. This narrowing of the sample distribution from the variable distribution is referred to as the central limit theorem, which states that if a sample with a sufficiently large sample size, the sampling distribution will approximate a normal distribution. Let us take a moment to refresh how these theories control our sampling distributions. First, the law of large numbers allows us to assume that by collecting enough samples, our sample mean will provide a good estimate of the population mean. And second, the central limit theorem allows us to assume that a large enough sample provides us a sampling distribution that will be approximately normal no matter what the population distribution looks like. Together, these theorems mean that even if we do not know the shape of our population distribution we are sampling from, we can draw inference about a population if we take enough samples to assume we are approximating the population mean and that the sampling distribution is normal in its shape. Now we will refresh the ideas underlying the Z and T distributions. Since each combination of population means and standard deviations results in a uniquely located and shaped normal distribution, where the shape is controlled by the standard deviation, we need to take advantage of this symmetrical shape to the distributions to determine the percentage of values that lies between 2 points in the distribution. However, to do this, we have to find a way to standardize the distribution. This standardization is called the standard normal distribution, which is a normal distribution where the mean equals 0 and the standard deviation equals 1. You might be more familiar with this being called the Z distribution. However, in order to use the Z distribution to determine these probabilities, we have to know the population mean and standard deviation. Generally, we do not know the population standard deviation and mean. Without these, our confidence level comes from the T distribution, which is derived from the T statistic. The distribution produced by the formula is a symmetrical curve with a mean of 0 that has its width controlled by our degrees of freedom, which equals little n minus 1. The differences we see in this set of curves results in the tails of the distribution having higher probabilities. If we compare the statistics from the Z and T distributions at a 95% probability, the Z statistic is plus and minus 2 standard deviations of the mean, while the T statistic requires us to define our sample size, and if we set it at little n equals 10, we get plus and minus 2.26 standard deviations of the mean. This means unless we have a significantly large sample size, that our T distribution will produce a larger confidence interval than the Z distribution because of the added probability in the tails. Let us recap how all of this impacts our ability to sample. What if I had to tell you to shoot at a bullseye without knowing where the bullseye was? This is the case in sampling since the bullseye is unknown, meaning assessing the accuracy and precision of a statistical estimate is not very simple. The spread reflects the precision of the process, but the holes from the arrows only provide an estimate of the bullseye's accuracy. A confidence interval allows us to estimate the true value, or the bullseye, without knowing anything about the population distribution. This estimation process belongs to the techniques of inferential statistics, which help us determine how well our sample approximates the population. More simply, it allows us to describe the range of possible values an unknown population parameter could have. Beyond estimating the parameters we are interested in, we want to be able to assess how effective and efficient a sampling procedure is at estimating this parameter. Essentially, we want to know which procedure will get us the best answer for the least work. When we look at how efficiently a statistic provides an estimate of a population parameter, two things interact to control this process: the population variability and the sample size. A general rule of sampling is that as a population's variability, or the range of possible values an observation can have, increases, the number of samples necessary to achieve a desired precision also increases. Meaning, the larger our population standard deviation is, the more samples we need to be precise. In a connected way, we can also say that as a sample size increases, the precision of our estimated population parameter will increase, meaning that at some sample size, there will be a decline in benefit to sampling anymore. The difference in thinking about this between stats theory and the real world is the recognition of constraints on our sampling process. Stats theory would have us sample until we hit diminishing returns in our accuracy. The real world would have us stop sampling when we hit a constraint to our sampling process.
When it comes to designing a probability-based sampling strategy, there are 3 requirements we need to meet. As we think through all the considerations necessary to create a sampling design, we have to evaluate if they allow us to meet these requirements. First, do we have some kind of random sample? Without some concept of randomness, you cannot determine the probability of selection and therefore cannot make statistical inference about your population. Do we have a measure of interspersion within the sample? Your sampling units need to capture the variability of the target population. This helps ensure that we have a representative sample being drawn. Generally in natural resource management, we do this by proportionally sampling things along the edge of a population and within the interior of a population to account for any differences in the environment. And finally, we need to ensure that our samples are independent. You need to make sure that your plots are sufficiently spaced apart such that you are not remeasuring the same information or that your samples do not have autocorrelation between them. In natural resources, we generally accomplish this by using what's called sampling without replacement. Our most simplistic probability-based sampling strategy is simple random sampling. Most often, when we talk about selecting sampling units in natural resource management, we are referring to selecting the location of a plot. When we are doing this, we must remember that an underlying assumption of inferential statistics is that any sampling design must ensure a known relative probability of each observation being selected and that the samples will be independent of the other selected units. This is the basis for a random sample. Although very similar, this differs from simple random sampling, which requires us to have a known equal probability for each sampling unit. When it comes down to actually designing a sample, our management objectives should tell us what we want to measure. However, knowing when to stop measuring is much harder and more important to determine. All of the sampling we conduct in natural resources needs to be statistically viable while remaining practical. When it comes to determining when to stop sampling, we have many possible options, including stopping when we have enough plots collected to provide whatever necessary precision we deem we need, or stopping simply because it's becoming inefficient to continue sampling, or stopping because we have answered our question, or because it's just becoming too expensive to continue sampling. Should we sample too much, we will have wasted time and money. If we sample too little, we will have high errors to deal with in our decision-making process. When it comes to our statistical approaches, preliminary data from simple random sampling can provide an estimate of variability and allow us to determine exactly how many plots we will need to achieve a desired precision level. An important aspect to sampling the natural world is considering how our sampling unit will influence how we see the population.
The scale at which we choose to view a population at influences the level of variability or range of possible values that we would expect to find. If we look at this set of 5 1/10 acre plots, they reveal samples of 2, 2, 4, 0, and 4 trees respectively. giving us a sample mean of 24 trees per acre and a sample standard deviation of 16.7 trees per acre, overall showing us a fairly highly variable population. But what would happen if we sampled the same population at the same locations with a larger plot size? If we look at the plots now using 5 1/5 acre plots, we now have samples of 4, 5, 7, 2, and 5 respectively, giving us a mean of 23 trees per acre and a standard deviation of 9.1 trees per acre. While we see almost no change in the sample means, there is a significant decrease in the sample standard deviation at the larger plot size. Using this larger plot size reduces the odds of us having extreme values within the sample.
The reason this can be an important consideration in sample size determination is that we may want to use one plot size in our sampling design, but may have some preliminary data from another plot size that we need to use in determining our population variability. Although it will only provide a rough way of scaling our plot size, we can use this formula to scale the variance of our original plot size into preliminary data against the plot size we want to use in our sampling design to get an estimate of variance at the scale we want it at. Now let us look at a way of ensuring we obtain a representative sample.
Generally, when we start talking about systematic sampling, there are two reasons we want to use the approach. The first is that in most situations, systematic sampling can obtain a more precise estimate of a population parameter than simple random sampling using the same number of samples. In this example, we see that although both simple random sampling and systematic sampling start with similar confidence interval widths at small sample sizes, the systematic sample confidence interval width narrows faster as we add more samples than it does with simple random sampling. The second main reason we use a systematic sampling approach, particularly in natural resources, is that this approach is very convenient for most field sampling exercises. When used well, this approach can help decrease travel time and also allow field crews to make field observations of the entire population as they move between sample locations. When it comes to defining systematic sampling, a relatively non-statistical definition could be to cover the ground in order to produce a set of observations which will average out more quickly than a simple random sample.
Now that we are thinking about how we select sampling units, let us look at stratification to see a more efficient way of doing this.
The basic underpinning of stratified random sampling is that we take advantage of prior knowledge about the population to improve our sampling design. Within this system, we seek to improve our precision by optimally allocating our sampling efforts into areas where we have homogeneous values. By taking advantage of our knowledge about the population, we are able to divide the population into strata of expected subpopulations, or strata with a known range of potential values for sampling. When doing this, strata must not overlap, and all areas of interest must be included. In the big picture, the only drawback to stratification is the increased effort needed for the bookkeeping of the data and computation of the statistics.
There are three sample allocation approaches we will look at. The first approach is equal allocation, where the sample size is set equally for each strata. The calculation for this process is fairly simple, where we say that the number of samples in each strata is equal to the total number of availables divided by the number of strata. The second approach to sample allocation is proportional allocation, when the number of plots per strata is proportional to the area of the strata. This process makes the sampling intensity equal for all strata, meaning that we sample the same proportion of area in each strata. The final approach to allocation is called optimal or Nyman allocation, in which the available plots are allocated by an equation that ensures that the standard error is minimized. In this case, the number of plots that a strata receives is proportional to its area-weighted standard deviation. When it comes down to it, though, in natural resource management, there are rarely a need to do anything other than proportional allocation. It has been said that the simplicity and self-weighting feature of proportional allocation are probably worth a 10 to 20% increase in variance. It is important to remember that the allocation process is simply a guide to determining how many samples each strata should receive. We must then use our judgment and determine if this allocation is the best way to meet our sampling requirements.